So today I will introduce you a remarkable quantum algorithm called the Grover's algorithm, which is proposed by an Indian-American computer scientist called Love Grover. The goal of this algorithm is to find a solution to the search problem using the smallest possible number of applications of the oracle. An oracle is just some operation that can identify the solution to the search problem, denoted by n here. It's like a function. Let's say if x now is the solution to the search, then we have ox is equal to 0. When x doesn't equal to x null and ox null equal to 1. The procedure is very simple. First, initialize the input to be all 0 state. Second, you apply head-mod gate to the input to change them into the minus state, which is just a superposition of 0 state and 1 state, with the same possibility of 1 over 2. Note that the plus state is very much like the minus state is, except for this minus sign will be changed into the plus sign. In the third step, we run Grover iteration for square root of n times. And lastly, we measure the output. This will give you x null with a very high possibility, very close to 1. I bet you are very confused to this point. And now I will tell you some basic notations with a simple example that only involves 2 qubits to be researched. The first notation that I want to mention is a qubit. It's a tensor product, which has already been covered in our lecture video. I don't want to spend much time on it since we have learned it, but I want to emphasize that if you do a tensor product between two 2x2 matrix, you will get a 4x4 matrix. If you do tensor product between a 4x4 matrix and a 2x2 matrix, you will get a 8x8 matrix. That is because you are multiplying the later 2x2 matrix with every single entry of the 4x4 matrix. Thus you will get an 8x8 matrix as the output. Okay, enough for tensor product. Now I would like to talk about the gate, the quantum gate. I think you are very familiar with classical gating, classical computation. We have already learned AND gate and OR gate in our C language program course. So quantum gate is very much like a classical gate. It's just to take some input and do some operations and give you an output with information of the input. So the first gate I want to talk about is a head-mod gate. So what is a head-mod gate? Basically, a head-mod gate is its function is it takes when it takes 0 as input, it will return the minus state as output. When it takes 1 state as input, it will return you minus state as plus state as output. So since the head-mod gate is a unitary matrix, it is reversible. If we apply head-mod gate on a minus state, we will get 0 state, and which is the same if we apply a head-mod gate on a plus state, we will get 1 state. So also, I would like to mention that in quantum computation, the head-mod gate can be represented by a 2x2 unitary matrix, which is this one. If you times head-mod gate to the right of the input, you will get the output state. So the next state I would like to mention is X state. So what is the X state is very much like an Hadamard state. The representation matrix for X state is 0, 1, 1, 0. So like Hadamard gate, if you multiply this unitary representation matrix to the right of the input, you will get the output state. Basically, what this X gate does is to flip the 0 state into 1 state in the superposition, flip the 1 state in the superposition into the 0 state. So the last gate I want to talk about is this control NOT gate, which is denoted by this symbol in quantum computation. This symbol basically means the first input controlled, not the second input. For a more generalized situation, we can actually have n input, and the first n-1 input controlled, not the last input. This solid point here means that only if all the first n-1 input, which is denoted x here, are all in the 1 state, will the last state, which is denoted by y here, flipped. Also, I would like to mention that the x state will remain the same as the input. For like if you have 0 state here, the output will be 0 state. And we will focus on the 2 qubit to be searched, and this is control NOT gate for the 2 qubit. For 2 qubit to be 2 qubit to be involved, 1 qubit control NOT the other. Note that in the generalized situation, if n-1 qubit controls the last qubit, controls not the last qubit, we shall have 2 to the n by 2 to the n size matrix to represent the control NOT gate. So this is the and just like the other 2 gates, you multiply the control NOT gate to the right of the input, you will get the output state. And the representation of control NOT gate is also unitary. And next, I want to talk about the inner construction of Oracle here. First, let's review our problem to be solved. We have 4 atoms, which can be represented by 2 qubits to be searched. The 4 atoms are 0, 1, 2, 3, respectively, and here these 4 pictures are the simplified inner construction for identifying the solution. Now I will pick one of these 4 oracles randomly to give you further instruction of further explanation of how the oracle works, the inner construction of the oracle. So we pick the one that can identify 2 as a solution here. Basically, we have a solid point and a hollow point here. We take 3 qubits as input, and this oracle is this inner construction of the oracle is very much like a controlled NOT gate, except for there's a hollow point here. This hollow point here means that the input need to be in the 0 state to make the last qubit input to flip. Therefore, this is Oracle for identifying the 0 1 state to the second atom. So just like I said here, we take since we take 3 qubits as input, we need a 2 to the 3 by 2 to the 3 set of matrix to represent this oracle. So how do we construct this 8 by 8 oracle? The columns represent the input and the row represent the output. Note that the order I wrote here is very important. It can't be changed. Basically, we first flip the third qubit input, and then we flip the second qubit input, and lastly we flip the first qubit input to construct this order. And we fill 1 and 0 in this form, and all the diagonal are 1 except for 2 diagonal here, because if the input is 1 0, the third qubit will be flipped to 1, and when the third qubit is 1, and it will be flipped into the state of 0. So this, and we fill in other cells with 0, and then we get a unitary matrix that can represent the oracle that can identify x naught equal to 2 as the solution. So now we can finally look at the Grover iteration. So how do we construct so Grover iteration is also an operation, so we can construct a unitary matrix to represent this operation. So how do we construct it? We see this is a picture for Grover iteration. We can separate this picture into 9 parts. 1, 2. The second part is the oracle. 3, 4, 5, 6, 7, 8, 9. So the parallel lines here means tensor product, and we multiply each step by just normal matrix multiplication, and then we can get the unitary matrix that can represent the Grover iteration. So this is first step, and we multiply the second step, which is the oracle, to the right of the first step, and we multiply the third step to the right of the second step, and we do it step by step, and finally we got a matrix unitary. Since all the matrix in the multiplication here, 1 2 3 4 5 6 7 8 9 are all unitary matrix, so the result of this multiplication must be unitary. And note here that this control NOT gate is a 4x4 matrix, just like I mentioned, and the tensor the A here is a 2x2 matrix, which is 1 0 0 1. It's a identity matrix, just like I mentioned above. The tensor product of a 4x4 matrix and a 2x2 matrix gives a 8x8 matrix. So we finally get the matrix representation of the Grover iteration. So thus we can run this algorithm on an IBM quantum computer, or furthermore we can write a simulate source code that can be run on a classical computer. lastly, I want to give you more intuition by this 2D picture of why we need to run square root of n times of Grover iteration. So this beta here basically means the solution. We talk about this picture in a generalized view. Suppose we have n items to be searched and m targets, and the beta here means the state of the superposition of all the solutions with the same possibility here, 1 over square root to m. The sum here is just the sum of all the solutions to the search problem, and alpha here is superposition that is perpendicular to beta, which is denoted by 1 over square root n minus m, and this sum here represent the sum of the non-solution to the search problem, and we can easily represent phi into alpha and beta with a very simple algebraic calculation. You can do it yourself. It is in this form. So what is Oracle do? What did the Oracle do? What is the first two steps of the Grover's iteration do? Basically, it's what it just do the mirror symmetry with respect to the alpha axis, and what is the rest 7 steps of Grover iteration do? Basically, it does a mirror symmetry with respect to phi. So now we know that it basically rotates the phi towards beta with respect an angle of theta. So the second and we apply the first 2 steps of the Grover iteration again, and we get the mirror symmetry of G with respect to the axis of alpha, and then we get called G prime, and then we do the rest 7 steps of the Grover iteration. We get the mirror symmetry of G prime with respect to G phi axis. Basically, it rotates G towards the beta axis with respect to an angle of theta. So we can find that it is very easy to find out that if we apply Grover iteration for k times, we actually rotate a phi towards the beta axis with an angle of k theta. Sorry. So we want since we want the output to be as close as possible to beta, so sin theta here is denoted by this term, 2 multiplied by square root of m times n minus m over n, and after arcsine function we can get the magnitude of theta, and we want the output to be as close as possible to theta and not exceed theta. We don't want it to be in this side. because this will cause some trouble when measuring the output in quantum computer. So we just take the floor of pi over 2 minus theta over 2 over theta here. And the floor function means the closest real number that is less than or equal to the input, since it is approximately square root of n over m. So with respect to if there's only one target with m equal to 1, we need to imply the Grover iteration for square root n times. And finally, I want to say that this is only a brief introduction of Grover's algorithm. There are many more deeper things that you can try to explore and understand about this algorithm. It is clearly has at least a time-saving advantage over the classical search algorithm, which needs n over 2 times of applying the oracle on average, while our quantum search algorithm needs only square root n. The advantage gap becomes larger as the database you search becomes larger. That's all of this video. Thank you.